am recording. So for those of you who were here on Tuesday, we did the first 13 questions in our practice review for the exam. Someone asked me on Tuesday how many questions were on the exam, and I kind of waffled a bit because I wasn't sure. I checked, and there are 13 questions on the exam. So there were fewer than I thought. Okay, and you'll have an hour and 40 minutes to do those. So again, the strategy is use this review as a guide of what you should be able to do. This review has a lot more questions on it than will be on the exam, but that's an attempt to show you a variety of things. I'm going to be doing, like I said, questions 13 through 24, but I reserve the right to skip ones that are kind of similar. Okay, so I want to show you a variety of, calculus on different types of functions. Okay, so in the essence of time, I may leave one or two out, but when I upload the work for sure, I'll have everything worked out. So I'm going to begin again by sharing my browser just to show you what I'm using since we have more folks on today than we had last time. Okay, I'm in week 8. Okay, and I am using practice for exam 2.pdf. If you download this file and take a look at it, it's got all the problems, and then it has just an answer key at the back that shows you what the solutions are. What I'm doing is actually working through all the problems to show you how to get those answers. And again, just for information purposes, here is your exam 2. Okay, and once you finish, I would suggest when you do your exam, write down as much work as you can. And then after you finish the exam and submit it, okay, either take photos or scan in your work. There are apps that will let you, on your phone, take a collection of files, a collection of photos, and create a PDF with them, which then you can upload here. Okay, so if you want to upload the photos, that's fine. Some of you have done that already. If you want to make a PDF out of it, that's fine, whatever's easier for you. But here's where you upload the work, and you can do that after you've done the exam. Okay, so I'm going to begin sharing my tablet with you, so just give me a moment and I'll get that started. Of course, I'd like to encourage you, if you've got any questions about any of the material that we covered since exam 1, which is primarily the stuff on using derivative rules, product rule, power rule, quotient rule, chain rule. If you've got any questions on that stuff, just bring it up, okay? You don't have to just worry about the problems I'm showing you. Okay, you can always bring up your own. Okay, now let me just share this with you. Okay, and you should see my notes, okay? And again, we finished with question 12 on Tuesday, so I'm starting with question 13, okay? And again, this is sort of an applied problem. It's related to physics, but physics is very heavily dependent on calculus as far as describing how things move, okay? As always, I'd encourage you, if you've got questions, feel free to type them in the chat. I have that open. Or if it's easier, just unmute yourself and ask. Okay, so you might remember when we talked about this, when we first introduced applied problems like this, the motion of a particle or an object along a path is called its displacement, okay? It's usually referred to a function called s of t, where t is time in whatever you're measuring time in. Here it's measured in seconds. And s of t is a displacement, and here the displacement is meters, okay? Now you might be thinking, why are you using the term displacement as opposed to distance that the particle travels? Well, distance is not a really precise term compared to displacement. The reason for that is, think of the particle as being at a starting line, okay? And it can be at a certain starting line, like maybe the x-axis. If the particle moves up, okay, in a positive direction, its displacement is positive. If the particle goes backwards, back toward the starting line, its displacement is negative. Okay, we normally don't talk about distance in positive or negative terms, okay, but displacement does definitely have a sense to it, a direction to it. Okay, now velocity is the rate of change of displacement with respect to time. Okay, you can even think of that in terms of you driving a car. If your starting line is your house, okay, and a positive distance is towards the West Coast, okay, it takes you so many hours to drive so many 100 miles to get to the West Coast, right? So your rate of change is going to be in miles per hour. So the way I would get that would be to take the derivative. Okay, so my velocity function, again, you have to think of velocity is the derivative of displacement with respect to time. All right, and again, displacement is the given function. I'll put that here, S of t, with respect to time. So I want to know, how fast is this displacement changing? Right, so there's kind of your little cheat sheet. So that's just simple because, again, my displacement function is a cubic. So when I take the derivative of it, I'm just going to use the power rule over and over again. That's going to give me 3t squared minus 12. Okay, and I just used the power rule over and over. Bring down the 3, drop the exponent by 1. Okay, pull away the 12, bring down the 1 that's on t. Okay, 1 times negative 12 is negative 12. When the exponent drops to 0 on t, t becomes a 1, and it's not in the final derivative. Okay, and as always, the constants don't give me anything. Okay, so that's my velocity function. Acceleration, okay, is the derivative of velocity with respect to time. You can think of acceleration as a rate of change of velocity. Namely, is the velocity getting faster or getting slower? Okay, we just use the terms in English of acceleration and deceleration. Okay, but those aren't physics terms. Acceleration is the only term you're using. And again, it has a positive or a negative sign on it. Okay, so acceleration is the derivative of velocity with respect to time. Okay, now if you think about what units acceleration has, you've got to think about velocity. Notice when I said velocity, the units, okay, it's a rate, so it's going to have output units on the top. Okay, my output units are going to be in meters, because that's what S of t is. Meters. Okay, and then it's got t units on the bottom, which is second. Okay, so velocity has units of meters per second. Okay, acceleration, let me just call this v, just to make it easier. Okay, okay, so acceleration has v of t units on top, which is meters, okay, per second. And then it has t units on the bottom, which is second. Okay, so the units for velocity are meters per second, which is, again, meters. If you think about the second that's in the denominator of the numerator, that actually winds up downstairs, multiplying the seconds that's already there. Okay, so units for acceleration are meters per second squared. Okay, just to show you, what this is called. And again, I can call this A. Okay, and this is going to be the second derivative of displacement with respect to time. That would be the derivative of velocity. So just differentiate it again. Okay, so pull away the 3, bring down the 2, drop the exponent by 1. Okay, and that just gives me 6t. Okay, so again, here are the actual function values. Okay. Now, again, they're asking you, when is the particle moving forward? Okay, now I said the particle moves forward, okay, when the position function, s of t, is increasing, right? It's going in a positive direction. Okay, it's increasing. So what does that mean? That means the derivative must be positive there. Okay, so how do I do that? One way to do that is to take your derivative, your first derivative, and say that has to be greater than or equal to 0. Okay, well, how can I do that? I can add 12 to both sides. That'll give me 3t squared is greater than or equal to 12. Okay, I can divide both sides by the 3. 3 is positive, so it doesn't switch any order of the inequality. So that gives me t squared is greater than or equal to 4. Okay, and then you've got to take the square root of this. Okay, and you're going to wind up with a situation where you've got t is going to be like this. You've got 2 roots. But remember, displacement is positive. You're interested in where it's increasing. Okay, so basically between 0, okay, and again, if I hold on, never mind. Yeah, I'm interested in only my positive root. Okay, so basically, I'm interested in where t is greater than 2, where t is less than -2. Okay, so basically, what I'm saying is it's going to be moving in a positive direction, okay, when the time is more than 2 seconds after it started. Okay, so I'm only interested in my positive answer here because negative time doesn't kind of make sense. Okay, I'm not interested in what happened before I started timing the movement of the particle. So basically what I'm saying is the function is increasing when t is greater than 2. Okay. Again, in all of these examples, you can kind of think of it as, you know, what's happening right at, again, I want this to be positive, so I technically shouldn't have included 0. I should have just made it greater than. Okay, because if you think about it, 0 is not positive or negative. So these should all be strictly greater than. Okay, so this is increasing when t is greater than 2. Okay, so that's when the particle is moving forward. Okay, so again, you want the derivative to be positive. Can anybody think of another way I could have done this? How else could I have found the values of t? Okay, for this part C. In part C. Can anybody come up with another way to do it besides algebraically? No? You could have graphed this, okay, and basically said, all right, where are the y values greater than 0? Okay, so basically you could let this part be, you know, basically say this is my function y, and where are those values greater than 0? For what t's are those? Okay, that's another way to do it if you're not comfortable doing inequalities with roots. Okay, but basically, let's take a look at that. Okay, I'm sharing my browser, so you should be able to see Desmos. Okay, so I'm going to graph that derivative. Okay, and basically, I'm going to call it x instead of t. Okay, so here's the derivative. Okay, I know a lot of folks haven't looked at quadratic inequalities. Okay, but take a look at this graph. This is a graph of the derivative. All right, and what we wanted to know was, where is y positive? Where is the graph positive? You can see it's positive. Okay, here's where y is positive. It's positive to the left of -2 and to the right of +2. Okay, so that's how you can check graphically. Check it graphically by graphing the derivative and seeing where y is greater than or equal, greater than 0. All right, everybody understand why y is greater than 0 to the right of 2 and to the left of -2? Okay, folks, can you give me some feedback? Okay, is this clear? Because again, I'm trying to give you options for doing these problems. You don't have to crank through a lot of algebra if you've got graphical tools. And personally, I think Desmos is an excellent graphical tool. Okay. Again, you're trying to answer the question. It's not a matter of trying to, you know, be the best human calculator. Okay. So again, if this business with the taking the root here was a little bit, I don't remember doing this. Okay. You can always do it graphically. Okay. So since this was the derivative, we want an increasing function, and you can see the derivative is above the x-axis when t is greater than 2. Okay, so now as far as the particle moving backwards, okay, that's going to happen, okay, when the position function is decreasing. Okay, what does that mean? That means s prime of t is less than or equal to 0. That means the y values are less than, and again, I'm making it strictly less than 0. Okay, let's take a look at the graph again. All right, where's my derivative negative? Okay, so look at this graph. Where is the derivative, which is graphed? Okay, graph negative. Okay, and I'm talking about y values here. Because remember, the y values of the derivative are tracking the slopes of the tangent lines of that displacement function. So where is it negative? Between what x values? These are t values. Okay. So just imagine these are t's, even though I graphed them as x's. Okay, between what t values? Yeah, between -2 and +2. See, the y values are down here below the x-axis. Okay, so again, we know that between -2 and +2, okay, that the particle's moving backwards. The -2 part in time doesn't make a whole lot of sense, so we're only going to say between 0 and -2. Okay, because -2 in the point of from the point of view of time doesn't make a whole lot of sense. Okay, it's before we started measuring. Okay, so between. Okay, and again, I can do it algebraically. I can say t is less than 2 and greater than 0. Okay, so again, here are the answers to these parts. All right, so what does this mean from the point of view of position? What it means, as soon as the particle starts moving, it moves backwards. Okay, that's how come we get this. From 0 times 0 to time 2 seconds, the particle's backing up. And then after 2 seconds, there's this instant where it turns around to 2, and then it starts zooming forward again. Okay, that's what you would take away from this. Okay? Questions so far? Okay. All right, now if they want to find the distance, now they're using this English word distance. Distance is not displacement. Distance is always positive. Okay, so imagine you had like a GPS tracker on your particle, okay, and it started zooming backwards and then it zoomed forwards and did whatever it did moving forward. What you would want to do is you would want to track the total distance it traveled, whether it was forward or backward, right? If I add up displacements, displacements are signed quantities. They're going to cancel out, okay? So I can't do that. I can't just plug things into S of t, okay? What I have to do is I have to basically split it into forward and backward motion like this. I'm going to build a table. And I'm going to just track the motion of the particle at each time t. Okay, and then it's asking me between 0 and 3 for t. Okay, so I'm going to put those values in. Right, so I have 0, 1, 2, and 3. And then I'm just using my calculator to evaluate the position function, which is this cubic up here. Okay, so this is t cubed, where is it? Minus 12t plus 3. Okay, so you can see if I plug in 0 for t, okay, this term drops out, that term drops out, and I get 3 for position. What does that mean? That means the particle starts out, when I start timing its motion, it is 3 meters in front of the starting line. Okay, so it didn't start at 0, it started at plus 3. Okay, now let's plug in a 1, okay, for t here. That's 1 cubed is 1, minus 12 is negative 11. Negative 11 plus 3 is negative 8. Okay, so you can see the particle zoomed backwards in that first second. How far did it travel? It went from 3 meters above the starting line to 8 meters below the starting line. That's a total distance of 11 meters, right? It had to back up the 3 meters that it was ahead to get to 0, and then back up another 8 meters. Okay, you can do this again like this, 3 minus negative 8, that's a plus 11. Okay, Everybody see how I did that? Okay, then I'm going to plug in a 2 here. Okay, 2 cubed is 8, right? Minus 12 times 2 is 24, plus 3, that gives me a negative 13. Okay, remember, for the first 2 seconds, it's going backwards, so it shouldn't surprise you. It's going backwards further. Okay, so to get from negative 8 to negative 13, that's another 5 meters, okay, that it went backwards. Remember, I'm just tracking distance. I'm not tracking what direction it's in, okay? And then if I plug in a 3, all of a sudden this cubic term is going to start to dominate the equation. What's happened, mathematically speaking, is the negative 12t was dominant while my t values were small. So I'm backing up. Now all of a sudden at 3, this term is going to start getting bigger and the particle is going to move forward. Okay, so 3 cubed is 27 minus 12 times 3 is 36 plus 3. Okay, this is negative 6. It's still negative, but take a look. To get from 13 behind the starting line to 6 behind the starting line, it had to move 7 meters forward. Okay, so in this interval, the particle's going backwards. In this interval, the particle's going backwards. In this interval, even though it's still behind the starting line, it's now moving forward because the numbers are becoming less negative. Everybody understand how I did that? Understand the process? Anybody questions about the process? Okay, so total distance traveled is 11 meters plus 5 meters plus 7 meters. If I add all that up, that is 23 meters. Okay, so the particle didn't actually, the displacement isn't all that different. It went from 3 meters in front of the starting line to 6 meters behind. Okay, that's a total displacement of 9 meters, but it actually traveled 23 meters in doing that. Okay, because it went back further and now it's coming back forward. Okay, everybody comfortable with the difference? Okay, with the difference between displacement and distance. Okay, again, I'm trying to figure out where you're getting stuck. Okay. All right, are you okay with the difference between displacement and distance? Okay. Because again, the first couple of parts of this are asking about displacement, and then this last part is asking about distance. No? Yes? Okay. The next whole bunch of questions are all pretty similar. They ask you to find maxima, minima, or absolute maximum, absolute minimum. Okay, so I'm only going to do a few of these, okay, because some of them are kind of repeats. You know, they're just there for practice. Okay, but I will upload my notes with everything. Okay, so when they ask you for an absolute maximum and an absolute minimum, okay, they will do one of two things. They will either give you an interval, okay, and that's X values. Okay, so from X is -1 to X equals 3, inclusive, including the endpoints. Okay, so we're including -1 and +3. Okay, so absolute maxes and absolute mins have to give you an interval. If they left off the interval, let me ask you a question. This is a cubic equation. From what you know about what cubic equations look like, if there were no interval given, would f of x have absolute maxes and mins. If there were no interval given on this function in 14, would the function have any maxes or mins? Absolute, like across the whole domain of the function. What do you think? Okay, I'm asking for feedback, so just vote in the chat, yes or no. Okay. All right, don't be shy, vote. There's a whole bunch of you on. I think there's at least, oh my gosh, there's 18 of you on, okay? So there should be a couple of votes in here. Okay, we're getting a mix. I don't want to give everybody a chance. Okay. Okay, everybody understand the question. If I didn't have the interval in the question, would this function have an absolute max and an absolute min? Okay, well, let's draw the function. Okay, it is a cubic function. Okay, and it has a positive leading coefficient. So aside from, you know, how stretched out it looks, it's going to look something like this. Okay. Absolute means, if I leave out the interval, it means over the whole domain of the function. Okay, that's what absolute means. It doesn't mean local. Okay, so you can see the way I drew this function, it has a local max and a local min. Okay, but if you're talking about the entire domain of the function, there is no absolute. Okay, no, there is none, because the function goes all the way down towards negative infinity here and all the way up towards positive infinity here. So there is no absolute max or min if the interval is left out. Okay, does everybody understand why that is based on the function? It has a local max and a local min, sure. Okay, that's fine. Okay, but no absolutes. Everybody all right with that? Questions? Okay, again, you have to know what the function would look like, and you could certainly graph it to see, okay? All right, I need to get rid of the picture because I need the room to work. So I'll just get rid of that temporarily. So how do we do this? Okay, the strategy for finding these is to locate any local extrema, local maxes and mins inside the interval. Okay, and I do that by taking the derivative and setting it to 0. Okay, remember, those are the places where the slope of your tangent line is 0. That's what it means to set the derivative to 0, is to find out where does the function f of x have a horizontal tangent? Where does it turn around? Those are going to be the local maxes and local mins. Okay, and then what you have to do is test the value of f of x at the critical points. Okay, so that's these. And at the endpoints of the interval. Right, so again, you may have the situation where your highest value is actually one of your interval endpoints. So you've got to check them off. Okay, so this is I've kind of just written out a cookbook strategy. Here's step A, here's step B. Okay, it's just 2 steps. It's not that involved. So the first thing I'm going to do is take my derivative. Again, I've got a polynomial, so I don't need to worry about any place where my derivative is undefined. Remember, in order to find critical points, okay, which are what I'm doing in step A, I have to figure out where's the derivative 0 or where is it undefined. Since it's a polynomial, its derivative will not have any undefined points, so I can ignore that. Okay, we'll look at an example where I do have to worry about that. Okay, so again, I'm just trying to get critical numbers or critical points if you include the y values. Okay, so let me just use the power rule over and over again. We have 2, I'm pulling that away, bring down the 3, drop the exponent by 1. I have a 4, pull that away, bring down the 2, drop the exponent by 1. Okay, I have a +2, bring down my exponent and drop it by 1, which gives me x to the 0. So that's a constant. Okay, so this gives me 6x squared minus 8x plus 2. Okay, that's my derivative. I need to set it equal to 0. Okay, the first thing I'm going to do is factor out any common factors. Oh, and by the way, okay, there are polynomial, I'm trying to put this in the chat, factoring applets online. Okay, there are polynomial factoring applets online. It turns out that this does factor, but it's a pain in the neck. Okay, I'll show it to you algebraically. Okay, I'm going to factor out my greatest common factor first. I'll work down so it's easier to follow. Greatest common factor is a 2. That leaves me 3x squared minus 4x plus 1. Okay, and again, you might remember, okay, the way you do this is there's only one way to get 3x squared, and that's to multiply 3x by x. Okay, this term's positive, which means I'm using 2 of the same sign numbers to get this product of 1. Okay, they can either be both positive or both negative. This basically says they have the same sign. This tells me they're negative. Okay, I'm lucky because there's really only one way to get 1, multiplying 2 negative integers, and that's -1 times -1. Okay, now if you FOIL this out, you'll see you're going to get a 3x squared minus 3x minus another x is the 4x plus 1. Okay, so again, that's doing it by hand. Okay, and then you set any factor that has an x in it equal to 0. Please don't set 2 equal to 0. That makes no sense. Okay, but suppose you weren't able to do that. Okay, you had forgotten how to factor. Okay, you just go online like this. Okay, and you search for polynomial factoring calculator. Look at that, first hit. I guess a lot of people use it. Okay, we've got a bunch. If I have a choice, I'm going to use Symbolab. Okay, one of my favorite sites. And then I can factor that polynomial. I can even leave my original numbers in it. Okay, it was 6x squared minus 8x plus 2. Okay, that was the thing that came out of taking the derivative. Ta-da, see it down here? Here's the factored polynomial. Okay, Not doing every step by hand is not cheating, okay? You are leveraging technology, okay, to do the steps that aren't terribly important. Yes, you have to know, I need to factor this, and I need to set every factor with an x and it equal to 0. But that's not the sum total of what you're trying to do. That's what you were trying to do back in Math 121, okay? What you're trying to do here is actually answer a question about where this function has maxes and mins. So this is just an intermediate step, leverage technology, okay? All right, enough said. Okay, so if you're looking at this saying, up, she lost me right here, I'm not going to be able to factor it. Yes, you can. Okay, it's called Symbol Lab. Okay, so use what you've got. And then you can see over here, I'm setting the factors with x's in them equal to 0. This gives me 3x equals 1, x equals 1/3, x equals 1. Okay, so these are my critical numbers. All right, and now what I'm going to do is, since they asked me for absolute maxes and absolute mins, I'm going to build a table. And I'm going to put my critical numbers and my endpoint intervals in here. All right, and then I'm going to evaluate f of x, which is the original function. Because again, I want to see where does it attain its highest x value, y value, and where does it attain its lowest y value. Okay, that's what a max and a min is. It's the y values of the function. Okay, so how many of these do I have? Okay, I have the two critical numbers from inside. So I have 1/3 and 1. And then I have the two endpoints of the interval, -1 and 3. Okay, so I'm just doing this on a calculator. And again, you can use the Web 2.0 calculator if you don't have a TI, okay, or you can use the TI if you have it. Okay, I'll do some on the TI and some with Web 2.0. So let me just share my TI with you. Okay, so here you should be able to see that. Okay, and I'm just going to take my function. And again, this would be real easy to do with a table on the TI, but I'll just show you doing it one by one. Okay, so here's 2 times 1/3 cubed. All right, so I need to raise that to the 3rd power. And then minus 4 times 1/3 squared plus 2 times 1/3 plus 3. Okay. Now that gives me about 3.29, right? 36. Okay. So I'm going to put this approximately 3.2963. Okay. So about that. And again, I'm sorry, my handwriting's starting to get away from me. Okay. So that's about what that is. Let's check some of the other values. Okay. You can just do second enter and plug in a 1 here. Okay, it would be easier for me to evaluate this at 3. Let me show you why. I just did second entry. And then I'm going to go back and I'm going to delete the 1 and the divide. And now I've got a 3 in there for my x value. Delete, delete. Delete, delete. There's my 3. And then enter. This gives me a 27. Okay. Now, again, if you want to evaluate this on the Web 2.0 calculator, okay, remember, this calculator will also show you fractions and whatnot. Okay, it's just typing it in that's a little bit harder to use. Here's the calculator. Okay, so I have my original function, and I'm going to plug in a 1. Okay, let me do -1 first. So this is going to be 2 times, you've got to do it like this, 1 and then negate it. Okay, so you have to put in the number first, then hit plus minus to change the sign. See how it works? It's like a toggle, right? And then that's raised to the third power. So there's the 2x cubed, then it's minus 4x squared. Okay, and I'm going to put in my -1, so 1 negative squared. There's a special squared key, so I'm going to use that. And again, you can see what it looks like up here. Okay, and then it's plus 2x, parentheses, put in the 1, make it negative. Okay, so 2x cubed minus 4x squared plus 2x, and the last term is plus 3. Okay, and then enter to evaluate it. That gives me a -5 when x is -1. Okay, and let's say I want to try it now for +1. That was one of my critical numbers. Okay, so I want to type it in, but without the negative signs. So how do I do that easily? Go click up here, and it'll put what you typed in back into the calculator. And all you need to do is go and backspace. Oops, nope, sorry. I want my backspace key. Sure, undo change. You can use backspace on your keyboard. That's what I'm using, just to backspace over the negative signs. Okay, I'm just using my backspace key on my keyboard. Okay, and then hit enter, and you can see that's not right. So -4. Nope. 2x cubed minus 4x plus 2x and plus 3. I lost the plus 3. There you go. Okay, somehow when I backed up, I lost the plus 3 at the end of the function. So 2x cubed minus 4x squared plus 2x plus 3. That evaluates to 3 when x is 1. Okay, so everybody see how to use both calculators? Okay, anybody have questions? I'm showing both of them because I know not everybody has the same thing. Okay, so back to my table. And I've written in the y values. Okay, I've written in all the y values. And then all I have to do is to go back and look at them. And I'll say, okay, what's the lowest y value? That's -5. So that would be my absolute minimum. Okay, and the y value is the absolute minimum. So -5 is the absolute minimum. Okay. If they ask for an ordered pair, you can type in -1 comma -5 in parentheses, but the minimum value is -5. And then the maximum value, the absolute maximum value on this interval, actually happens, okay, at the left endpoint. I mean, the right endpoint. Okay. And that's 27. Okay, so you can see here the two critical numbers we got, the 1/3 and the 1, they're not absolutes. Okay, this function actually has its lowest y value at the left-hand point on the interval and its highest y value on the right-hand part of the interval. Okay, so it kind of may look something like this. Okay, where you've got -1 over here and a 3 over here. And you're going to wind up with a function that kind of looks like this. Maybe it has a like this. So you can see the lowest values here, the highest values here, even though it does some stuff in the middle. Okay, so don't assume that your critical numbers are going to give rise to the absolutes. Okay, you've got to test the endpoints. Okay, how about this? Questions? Any questions on 14? Questions on 14? Sense? Okay, I'm going to do 15. Okay, only because 15 is a different type of function. Okay, and I know it's a lot easier to do this stuff with polynomials, but let's try one with a rational function. Okay, so this is a rational function. Okay, and you know from experience, rational functions have undefined spots, namely places where the denominator is undefined. It turns out you may look at this and say, oh, well, this is going to be undefined when x is -1. It's not, because when you square a -1, you get a positive, okay? There are no values that are going to make this denominator undefined, because there's no way to get x squared to be a negative number, okay? So it's an unusual rational function in that there's no undefined spots, okay? Now, they're giving us an interval that goes from -2 to 2. So we're going to do things the same way. We're first going to take the derivative of the function and see if we have any critical numbers. Okay, and the critical numbers we may have to check if f prime of x is undefined anywhere. And again, I'm saying that only because I'm starting out with a quotient. Okay, I may need to check. It's not a polynomial. It's not well behaved like a polynomial. So let's check. So again, if you take a look at this function, you can see it's a quotient. There's no real easy way to get around that fact. So I'm going to use, so in other words, what I'm saying is I can't do anything algebraically slick to turn this into something easier to work with. So I'm going to use the quotient rule. Okay, and that's basically says if f of x equals u over v, f prime of x equals denominator function first, okay? So denominator function times derivative of the numerator minus numerator function times derivative of the denominator all over denominator squared. So there's my pattern for the quotient rule. And again, what I recommended to you last time is there is when we first started introducing rules for differentiation, there's a cheat sheet of derivative rules and examples. You can use that, okay? But I would encourage you to make up your own, okay? So you have it handy and it's comfortable for you to use. It's real hard to use somebody else's notes. So make up your own with just, here's the power rule, here's the product rule, here's the quotient rule, here's the chain rule, maybe with a little example. Okay, so you're comfortable and you don't have to shuffle through your stuff to figure out, okay, how do I do this? You've got it right there. Okay, so there's my quotient rule, right? And then I have u is my numerator function, which is 3x minus 4. And v is my denominator function, which is x squared plus 1. Okay, these aren't strange or they're both polynomials, okay, and there are no compositions. So taking the derivatives are pretty straightforward. This is going to just give me a 3. Okay, bring down the 1 that's the exponent, multiply the 3. The exponent becomes a 0, x disappears. Okay, this is going to give me 2x. Okay, and then plugging it into the pattern for the chain rule. That gives me v times u prime, which is 3, minus, okay, the u times v prime, whole thing over v squared. Okay? Now again, because I'm going to have to play with this. Okay, namely, what do I need to do now? I need to set this thing equal to 0 and figure out if there are any x values that make that happen. Okay, so see this mess up here in the numerator? I want to simplify that, only because I'm going to do more work on this function. So I'm going to do a little bit of algebraic simplifying. Okay, so the first thing I'm going to do is multiply everything in that first set of parentheses by 3. Okay, and then I'm going to multiply everything in the second set of parentheses by 2x. Okay, but remember, you've got a minus sign out here. Okay, so basically you can think of it as multiplying each thing by -1 times 2x or minus 2x. Okay, so 2x times -2x times 3x gives me -6x squared. Okay, and -2x times -4 gives me +8x. Okay, so I kind of did two algebraic steps there together. I distributed the minus and I also multiplied by 2x. If you want to break it into two steps, leave the parentheses in place, and then you'll get minus parentheses 6x squared minus 8x, and then you have to distribute the negative sign last. Okay, I did them all at once, okay, just to cut down on steps. The denominator is still the same. Okay, and then the rest of it is just collecting like terms. Okay, the only like terms I have are in x squared. Okay, so I'm going to start with my 3 minus 6, or rather minus 8x. X is the linear term, minus plus 8x, plus 8x. And then minus 3x squared minus 6x squared negative 3x squared. I'm just writing them in that order because I feel like it. You could write it as negative 3x squared plus 8x plus 3. No difference. Okay? So I just combined the like terms here. All right, well, that looks a lot easier to work with. Now I can set my derivative to 0. And see if I get anything out of this. Okay? All right. Well, if the first step is going to be to try to get rid of the denominator, so I'm going to multiply both sides by the denominator. Okay? And you can see it goes away over here, thank goodness. And I'm multiplying it by 0 on the left, so it stays 0. Okay? So that was good news. I didn't have to deal with that messy thing squared. Okay? Feeding it to the 0 on this side just got rid of it. Okay, but that means I still have a quadratic. Okay? So what can I do with that? I can leave it on this side, right? And then simply just move the terms around. Okay. So let's put my squared term first because you're used to seeing it that way. And remember, you can move terms around as long as you take the leading sign with the term. There's a minus in front of 3x squared. So if I put it first, it needs to have a negative sign in front. The 8x is positive. 3 is also positive, even though we don't write the plus sign when it comes first. Okay, the next thing I'm going to do is factor out a -1. Why am I going to do that? Because I don't like starting my quadratic with a negative term. That's going to flip all of the signs on all of the terms, but not change the numbers. Okay? And guess what? I got rid of my problem. all right? Because this -1 out here is not going to give rise to any solutions. There's no x, okay? But I made my quadratic look more like what I'm used to, okay? Don't be afraid to use the rules of algebra in order to simplify things, okay? I know it's never been presented to you that way, but the point of algebra is to make things easier to work with, okay? So that's what I just did here. I did some algebra, got rid of the denominator, and then I said, you know what? I'd rather have my squared term first, but I don't want it to be negative. So I moved the terms around, and then I factored out the -1, and now I have a normal looking quadratic, okay? You know, and I know, we can use the Symbolab factoring calculator to factor this, okay, if it's factorable. If not, there are calculators online that will run the quadratic formula for you, okay? So again, don't feel you have to do all of this arithmetic stuff by hand, okay? Turns out this one is factorable. I'll save you the trouble of looking it up on Symbolab. Okay, and you can see if you quickly FOIL it, this is going to give you 3x squared. Okay, then you get -9x plus 1x is -8x, and then +1 minus 3 gives you the -3. Okay, set each term with an x equal to 0. Okay, and this will give you x equals -1/3, x equals 3. Okay, so those are my critical numbers. But I said I should have checked to see if my derivative was ever undefined. So here's my question. Is this ever undefined for a value of x? Okay, again, it's got a denominator in it. So take a look at the derivative and see if you can answer the question. Is f prime of x ever undefined? Okay. And this is what I'm looking at right here, where my cursor is. What do you think? Is there any value? Okay, me is saying only when the denominator is 0. Can this ever happen? Okay, so can the denominator ever equal 0? Okay, how do you do that? Play with a couple of x values. Play with some simple negative values for x, like -1. Okay, if I plug in a -1 here and I square it, it becomes +1. Then I have 1 plus 1 is 2, 2 squared is 4. Okay, if you pick a larger value, a negative value, not a larger, but a more negative value, say like 5, -5. -5 squared is 25. 25 plus 1 is 26. 26 squared, some big number. Okay, pick a positive value of x, like 1. 1 squared is 1. 1 plus 1 is 2. Okay, 2 squared is 4. Okay, fractions aren't going to help at all. Okay, because of the squaring, and because of the positive side, sign inside, and the plus sign, the denominator can never equal 0. Okay, you ought to be able to tell that. Okay, you ought to be able to tell that. The only way you'd be able to make this 0 is if you plugged in an imaginary number, and we're not working in the imaginary number system, okay? Okay, because of the squaring, which makes whatever x you put in positive, and because this is a plus and not a minus, okay, this can never be 0. So my answer to this question is No. All right, I don't need to worry about where the derivative is undefined. So let's take a look at what I have. Okay, I have critical numbers. Okay, I have a critical number of -1/3. That's within this interval, right? Between -2 and +2. What about this critical number? Okay, is this value in my interval? Is this value in my interval? What do you think? I'm asking a question, folks. No, it's not. It's outside the interval. So it's not a candidate for an absolute max or min. We should have checked that up here as well. Okay. But both of our critical numbers in this one were within the interval -1 to 3. Okay. So that wasn't a problem. But this example shows you need to check that your critical numbers are actually in the interval of interest. Okay. So again, no, don't use. Don't use it because again, we were specifically asked about the interval. Okay, so I'm going to do the same kind of table again. I'm going to put in my x values on this side. And then I have my f of x here, which is the original function. Okay, and I'm just going to evaluate. I've only got 3. Okay, I have -1/3, -2, and +2. Okay, I threw away the 3. Okay, and again, do the same trick. You can pull up your calculator and you can plug in your values here. Okay, just if you do this on your Web 2.0 calculator, make sure you parenthesize the numerator, parenthesize the denominator. Okay, I'm just going to show you briefly how this works. Okay, I'll bring up the TI first of all and turn it on, clear it. Okay, so for this one, I maybe want to do alpha y equals numerator and denominator, so I get a fraction. And then I have 3 times x, and I'm going to put x in as a fraction. Okay, if you do that on your TI, okay, so you can nest these things. I'm going to say -1 on top, 3 on the bottom, arrow out, close the parentheses. Okay, if I do it like this, the calculator will keep the answer as a fraction. Okay, and then this is going to be parentheses, alpha y equals -1 divided by 3. Yes, you can put the negative sign out in front is if you prefer. It's easier to type it like this. Square this. Okay, +1. Right, and then hit enter. I get -9/2. Okay. And again, like I said, if I were doing this on the Web 2.0 calculator, I'll try that with a -2 example so you can see it. You need to put parentheses around the numerator and denominator. Okay, so let me show you that real quick. Okay, so I'm clearing this. Okay, so open parentheses for my numerator, and that's going to be 3. And again, since the 2 is a +2, I don't need parentheses, but I'll use them anyway. So that was 3 times 2 minus 4, close parentheses on the numerator, divide, open parentheses on the denominator. Okay, and then this is going to be 2 squared. Okay, I got a separate squared key, +1, close parentheses on the denominator. And take a look at the rendering, okay, and make sure it looks like what you have written down. Okay, so this is 3x minus 4, and this is x squared plus 1. All right, and that gives me 0.4, okay, which again is 2/5. Okay, so I'm going to go back here. Okay, this is 2/5. And I'll save you the trouble of doing -2, -2. All right. So now you've got an interesting situation. You've got a bunch of fractions. Again, you can evaluate them, okay, as decimals. Okay, if you want to see, all right, well, what are they really like? -9/2. I'm not so sure. Math, des, enter. Oh, that's -4.5. Okay, so that's -4.5. This one we said was 0.4, and now we have -2. Okay, so if you want to do everything as decimal, that's fine. You can see this is your absolute minimum. Okay, and then this is your absolute maximum. And again, this was incorrect. I didn't need to put that in. This was -2. Yeah, that's right. Okay, so my absolute maximum is this one. Even though 2/5 is pretty small, it's the only positive value. Okay, so that's how you do those. Okay. All right. Okay, so let's take a look at one more. Okay, and then this is kind of like the problems that were in the last homework that you guys did. And I noticed that quite a few of you left these problems out. Okay, these were the ones that said, tell where the function's increasing or decreasing, find the local maxes and mins, talk about concavity, and then graph the function. There were 2 like that in the last homework, and a lot of folks left those out. Okay, what I'm trying to show you here is don't leave them out. Okay, see if you can figure out how to do them. So I'll do 16, and then the ones that follow this are very similar, so I won't spend time on those. Okay, so intervals of increase or decrease. Okay, this is where you use f prime of x. Okay, local maxes and mins. Okay, you can also use critical points. Okay, and you can use the second derivative if you want. Okay, but we'll be able to use the stuff from part A there. Here I'm going to use f double prime. Okay, so that's kind of like my rough idea of how I'm going to approach the problem. Okay, so here, what I'm going to do is differentiate the function. And again, I'm not going to go through how I'm differentiating. If you've got questions about what I'm doing, please unmute yourself or type in the chat. Okay, so there's my derivative. Okay, set the derivative to 0. I'm going to try to find the critical numbers, namely where the function turns around. Factor out my common factor. Okay, this one's pretty easy to factor. Okay, so this gives me that. And then set the factors with x equal to 0. Okay, so those are my critical numbers. And the way I tell increasing and decreasing is I draw an X number line and I put my critical numbers in there. Okay, so my critical numbers are 5 and -1. So here's -1, here's 5. And that kind of divides the number line into intervals. Okay, so here's the first interval, -infinity to 1, not including, -1 to 5, and 5 to positive infinity. Those are my 3 intervals. And then you pick a test point in each interval. This is up to you. Pick whatever is easy to work with. All right? And then check the sign of the derivative. All right, so here's the derivative. Okay, I'm kind of running out of room here, so I'm going to work up on the top. In my first interval, I might pick f prime of -2. Okay, that's in this interval here, the leftmost interval. And I'm just plugging it into the derivative, and I'm trying to figure out what's the sign of the derivative. So I'm going to use the factored form of the derivative. Okay, so I'm using this over here. Okay, and then my other factor is x plus 1. Okay, and I'm just looking at signs. I have positive, negative, negative. Okay, so that means in that interval, the derivative is positive, because when you multiply 2 negatives and a positive, you get a positive. Okay, then the second interval, oh, I'm definitely going to pick 0 there. Plug it into the derivative. Okay, check the signs again. Positive, negative, positive. That's negative, right? Because we've only got an odd number of negative signs in the product. And then the last one is going to be, oh, probably 6, only because it's close to 5. So this is 3 times 6 minus 5, 6 plus 1. And I think you can see these are all positive. So the sign's positive in this interval. Okay, so again, I'm just checking the sign of the derivative at a test point in each interval. Now remember, when your derivative's positive, your function's increasing. When it's negative, your function's decreasing. Okay, so my answer to this part would be increasing on 2 intervals, -infinity to -1, or 5 to infinity. Okay, and I'm writing it with interval notation, sorry. And then it's decreasing on the interval in the middle, and that's from -1 to 5. Okay, everybody see how I did that? Just using the sign on the derivative, and you just pick points on either side of your critical numbers. Okay, so the first thing I did was draw the number line, put in the critical numbers, divide it into intervals. Okay, then just pick a test point. You can even do this part on your calculator. Okay, and just decide positive increasing, negative decreasing. So here's the answer to part A. Okay, now this will also tell me what gives rise to the maximum and minimum values. I know one will be at where x is 5. So I have 5, f of 5. Okay, and again, I did this on my calculator ahead of time. Okay, so I know my y value, which comes from the function, is -96. How did I get that? I went back here and I plugged in 5 for x, and it came out to be -96. Okay, and then the other one is -1, f of -1. Okay, that's -1. Okay, when I plug -1 into my function, okay, I got a 12. Okay, now again, you can guess that, well, this must be the min and that's the max. How else could you tell? Take a look at the increasing, decreasing. You are increasing up to f of -1 and decreasing away from it. So yes, this is going to be your max. And if you take a look at f of 5, you decrease down to it and increase away from it. So this is your min. Okay? And again, remember the actual values of y are the maxes and mins. Okay? Okay so far? Okay so far? Yes? Okay, intervals of concavity. That's my second derivative. Okay, so I'm going to start with my first derivative. And I'm going to differentiate it again. Okay. Your inflection points are likely to be where your second derivative is 0. Okay, this is linear, so it's super easy to solve. Add 12 to both sides, divide by 6. This is an inflection point. Okay, and your inflection point will help you do the same thing. You can draw a number line. These are x values. And you can put your inflection point here in the middle. And you can see these are going to tell you intervals of concavity. -infinity, 2, 2 out to infinity. Okay, and again, pick test points and put them in your second derivative. Okay, so I'm going to pick a test point in the left interval. I'll pick 3. Okay, and that is okay, so that you can see is 18 minus 12. So that gives me a positive value. And again, you might remember how concavity works, right? Positive is concave up. All right, and I'll pick another value in the second interval from 2 to infinity. I'm going to pick 0. That's negative. And you might remember negative is concave down. Okay, so essentially it's concave up from -infinity to 2, concave down, right from 2 to infinity. Okay, everybody good with that? Okay, the inflection point has an x value of 2, and it also, if you plug it back into the original function, you'll see the y value there is -42. Okay. Asymptotes, okay, it's a polynomial, so it has none. Okay, and then what I need to try to do is sketch the curve. There is nothing stopping you from graphing this in Desmos and trying to copy the curve, but you actually have enough information to sketch the curve. Okay, we have a local maximum at -112. Okay, we have a local minimum at 5, -96. And again, I'm just guesstimating. Okay, so there's that. It changes concavity somewhere in between. So let's call that 5, let's call that 2, let's call that -1. Again, I'm just trying to draw them big enough for you to see. Okay, so I know that up until I get to my first critical number, the function is increasing. So it increases up to that maximum. So it must look something like this. Increasing up to the maximum. Okay, then it's got to decrease down to the minimum. So it's going to turn around and come down, and it's going to shift from concave down to concave up. Where? Okay, at 2, -42. Okay, so here's my shift in concavity. Right, so it's going to go down like this, and then become concave up. Okay, and you can see it increases out from 5 to infinity. Okay, that would be an accurate enough graph. Okay, if you were to draw this, okay, just again, kind of label your points here. Okay, if you can. I know the graphing tool, when you're trying to do it with your finger, is not fantastic, but try to get a shape that looks like that. Okay, so questions? Questions on this?
When you were testing the inflection point,
Yes.
when you used 3, shouldn't that have been because when you graphed it, you graphed it from concave down to concave up, but right here you wrote concave up to concave down from negative infinity to 2.
Right, but at 3, you can see it's concave up. Right, 3 would be here, and that's past where it changes concavity. Okay, the actual inflection point is at 2. Okay, where it's going from concave down. Oh wait.
Yeah, you see what I'm saying?
Yeah, it's backwards. Concave up. My bad. Thank you.
No problem.
Let's see. Okay, let's see if we can fix what Julian found. All right, let me get rid of some of my scribbles. Okay, concave up and increasing.
Or I think you graphed it right, but did you just notate it up here wrong?
Okay, hang on. This is positive though, right? Because it's 6x. And if I put a 3 in there, oh, I notated it wrong. I put it on the side. That's what you're saying.
Yeah, you graphed it right, but right here you notated it wrong.
That's backwards did here. Yeah, gotcha. Okay, everybody see what he found? Okay, here's the 3, and this is where it's concave up. Okay, I put it on the wrong side of the number line. Thank you, Julianne. Okay, so again, I went and picked my positive side first, and instead, so here's the 0, and here's the 3. Okay, sorry about that, folks. Okay, so again, what he said is right, and I did have it graphed right. I just had it wrong on the number line. Okay, so again, here is the point where the concavity switches. Okay, and again, the only thing that was backwards were where I had the plus and the minus. Okay, so negative when x is 0, positive when it's 3. Okay, so here's what it should look like. Okay, so just had the words up and down backwards. Okay, so again, increasing up to this part was right, increasing up. Okay, and you can see it's concave down on this side of the interval. And then the concavity changes here at the inflection point. Okay, and it's decreasing downward to the minimum. Concavity is now concave up, and then it increases out. Okay, so thanks again. Thanks for pointing that out here. Okay, the words were backwards. Okay, but everything else was okay. Everybody all right with that? Okay. All right. The last thing I want to cover, and I know we're kind of running out of time, I just want to cover the applied problem. Okay, and that's kind of from 19 to 23. Okay, and that will be really quick. I'll upload all my work for these so you can see, and I will double check there are no, misspellings or things that are switched. Okay, I just want to make sure everybody knows how to do this type of problem. Suppose the demand function for a product is given by d of n equals negative 0.5 n plus 440, where n is the quantity of items in demand. Okay, and d of n is measured in dollars. So that means D of N is a price. Okay, and then this is a quantity. Okay, everybody good with that so far? Okay. Suppose each item costs $14 to produce and the fixed production costs total $2,400. Okay, so each item costs $14. This is your variable cost. And it depends on N, right? It depends on how many you make, right? And then this is a fixed cost. So this is a number, just a constant. So if you want to figure out costs as a function of N, it's your fixed cost plus your variable cost. Okay, fixed plus variable. All right, we good? And then they want you to evaluate that when you make 200 items. So just plug in 200. And again, use your calculator to do the arithmetic. That gives me $5,200. Okay, that's the cost to make 200. Now they want us to know what is the profit function from the sale of N items. Okay, so profit is revenue minus cost. Okay, but I don't have I have a cost function, but I don't have a revenue function. So revenue is your price times the number demanded, right? You sell them for however many dollars each, okay? And then you've got so many of those that you want to sell, okay? So that would be your price function is your D of N, which is negative 0.5 N plus 440. And the number demanded is just N. So that means my revenue function is the same as my price function, except everything has one more of the variable in it. So this becomes N squared. And this becomes 440N. Okay, so that's how you develop a revenue function when you're given a price and a demanded amount. Okay. Okay, remember my banana example. If bananas are 10 cents a piece and there are 8 people who want to buy it, your revenue is 80 cents, 10 cents times 8. Okay, so it's that simple. All right, now your profit. You're going to put in your revenue first. And then you're going to subtract the cost. Okay, and again, please remember to put the cost function in parentheses because you want to subtract both terms. Okay, so there's revenue minus cost. Okay, once I do the subtraction, okay, I'm going to distribute the negative sign to both terms here. Okay, so I'll wind up with a minus 14N, which I can then combine with the 440N. And that'll give me negative 0.5 N squared. 440 minus 15 is 14 rather, is 426 N minus 24. Okay, so there's my profit function. Okay. And again, if it's a matter of how many items must I produce and sell to make a profit of 3,000, okay, you start with your profit function and you put in 3,000 here. Okay, like that. And then you solve for N. The first thing you want to do is get rid of the 3,000 over here. So subtract 3,000 from both sides. That gives you 0 equals negative 0.5 n squared plus, okay? And then this would be minus 5,400. Okay, if I look at these coefficients, am I going to try to factor this? What do you think? No, absolutely not. Okay, so use quadratic formula. Okay, online calculator. Okay, you could certainly do it with the TI-84, but why would you when there are apps that will do it for you? Just plug in your function, okay, and it will give you 2x values. Okay, so you get 2x values. Let me see if I can do that really quickly. Okay, so calculator soup, that's a good one. Okay, so my A coefficient here is negative 0.5. That's on my x squared term. The B coefficient is 426. And my C coefficient is negative 5,400. Calculate. Okay, and again, I can see I get two x values. I get a negative 1. Okay, I did that. Yeah, this is supposed to be a negative value. That's right. Okay, it's negative 0.5. Calculate. That'll switch them around. Okay, so negative 0.5 on the squared term, 426 that's positive on my n term, and negative 5,400 is C. So you can see I've gotten two values here. Okay. And basically, I would have to, again, check that these both work. Okay. So I could make 12 of these or 839 of these or 840 of these. Okay. Either one of those should give me the profit that I want. Okay. And it shows you how to do the steps. Okay. Now, I'm not going to, write that down here. How many items must we produce and sell in order for our marginal profit to be 0? Okay, this is basically marginal profit, okay, is P prime of n. Okay, so you would differentiate that. Okay, so essentially, if I bring down the 2 and multiply it by the negative 0.5, I get negative 1n. Okay, and then this will just be plus 426. Okay, I just differentiated P of n. 2 times negative 0.5 is negative 1. And then 426 is the constant part. I want this to be 0. Okay, I'm going to add n to both sides, and I get n equals 426. Okay, and then in order to say what should the selling price be, okay, you plug in order for marginal profit to be 0, well, you know how many you have to sell to get your marginal profit to be 0. Okay, so plug 426 into your price formula up here, okay, which was D of n. Okay, so that's D of 426 negative 0.5, 426 plus 440. Okay, so when you have a demand of 426 units, your price should be $227. Okay, so what I'm asking you, the arithmetic here is really simple. Do you understand why I did what I did in each step? You understand why I did what I did in each step? Okay, and again, leverage the busy work. Okay, leverage the busy work. Okay, everybody good with this? Okay. right? I'm gonna come back to the meeting and ask if you've got questions on anything. Now, I know I left some things out. Okay, that's fine. If you decide to go over this review, once I upload it with all my work in it, take a look at all of the problems, including the ones we didn't get to, because we're at time. Okay, and make sure you ask me about them. They say, hey, number 18 on the review, I tried it myself and I couldn't get your answers. Okay, please go over this review. It's the best way to study for the exam. Right? Like I said, there's 13 questions on it that are very similar to these, and you'll have an hour and 40 minutes to do it. Upload as much work as you can. Okay, I will go through it and regrade everyone's exam. So don't be upset by whatever grade you get on it. Okay, your final grade will be higher. Okay, so